things that I will cover. Why is it that we believe in QCD? What is the evidence? Whatever you think you remember that took us to believe that the gauge theory of color is actually the theory of strong interactions. Okay, which has to do with the following questions. Okay, after all, you know what the situation is. The quarks are imprisoned forever to live inside these bags that we call proton and neutron and other mesons and baryons. And yet when we probe them, these bags with fast-moving electrons or neutrinos, quarks behave like crazy. So how is it that we actually believe in this picture? And we have accumulated a lot of evidence, which is fairly good numerically. Okay, what are the features that took us to this quantum chromodynamics, right, gauge theory of color? So we'll ask questions. Why do we believe in color? Well, that's easy, right? Everything we compute agrees with three colors. So today it's very easy to answer that. After all, you've been doing your homework, in which you computed things. But you remember the original sort of how the color was introduced? Why?
There was one baryon.
It was a strange baryon which was doubly charged, delta plus plus, which is 3 up quarks. And in order to have an anti-symmetric wave function and so on, we introduced color, right? So we wrote it. I'll comment on this in a second, why this is invariant and the color. Okay, there were other evidence. For example, there was a pi 0 decay into 2 gamma. That goes through that we should imagine like going through the quark loop. After all, pion is, I'm thinking like sort of a Higgs. Pion is a bound state, so if you think of it, it's the reason it happens because there are quarks inside. So when you calculate the decay rate, okay, you measure the number of colors. Okay, there was also, and this was a little later, there was a thing, very interesting thing, the ratio of EE bar cross section going into hadrons by EE bar going into muons. Very good, so you remember. And imagining that it is made out of quarks. And by the way, this is how this interesting picture of sort of confined quarks, which are at the same time moving freely, okay, starts. This would be counting the number of, if it goes through quarks, the number of, let me call them EQ, the charges of quarks that contribute, okay. By EQ, I will mean the quark charge. This is in the quark picture. Hadrons are made out of quarks, so what I'm really computing is EE bar going into QQ bar. Okay. It's a little strange that I get a actually correct result because after all they are this shopping bag. So what happens is, okay, this is what we call a jet picture, right, which emerged in analyzing this. That when I go through EE bar and produce this pair, QQ bar, say, with some angle theta, right? They will, of course, if this is true that they behave almost as free particles, they go away. And if they have a lot of energy, they will have a lot of energy go away from each other, okay? So what's going to happen? How does this, what we call hadronization, the jet picture, takes place, okay? As they separate, they will be slowing down because of the interactions with the gauge bosons, the radiation that they go through, the strange potential between them. As they slow down, the coupling, the QCD coupling gets stronger because you go to the distances, to lower energies and the bigger distances. So it's sort of, they form these hadrons. We'll have to talk about it, okay? I'm not explaining now, okay? Which we call jets, okay? This is what we have to understand. This is the lecture of today and tomorrow, understanding the things which agreed very well with the experiment at the time. So when this evidence accumulated, at the same time, this was late 60s, early 70s, there is a huge understanding, huge progress in understanding the evolution of coupling constants with energies. Okay. Something which goes under the name of renormalization group equations, which is the cornerstone of modern particle physics. And it has to do with the following. Remember when you compute the typical renormalization that we call the vertex correction type diagram, okay? This, it turns out, cancels with the other one, but they're all also at the same time. There is this, then there is this, and so on. Okay, these two actually cancel. So the message here is that E is E0, the bare charge, 1 plus some coefficient, E0 squared, logarithm, lambda. If I do this at some mass scale mu, the way I say, since there are this logarithm, I will get to this. Right? This is what you learn. This is the famous renormalization of charge. Right? E0 cube. By the way, since I'm doing it in leading order, I can also write E here later on, okay? It doesn't matter whether I write E0 or E, because the difference is small. So if I compute E of mu2 minus E of mu1, what will happen? The divergence will disappear. This quantity is actually physical. This is what I was telling you when I described the beauty of this field theory, renormalizable field theory, is the following. When I describe processes at different energies, I actually have one and the same description of these processes, except that the coupling constants will not be the same. But since they are physical, these differences, okay, this I just absorb. I say that this is my charge. And remember, the infinity that apparently we get probably will not be infinity, because the field theory will eventually break down, okay, whether it's the gravity, strong picture, string picture, whatever. This becomes calculable, and this is something of order E cube logarithm mu2 over mu1. I don't want to write this coefficient and even discuss it here. Let me just tell you that the correct formula, the way we write it, which can be generalized to any theory, not just QED, we write it like this. Well, let's say mu2 I call. The same thing, let me write the way it is conventionally written. Alpha is whatever coupling constant I'm talking in question divided by 4 pi. Okay, this was sketchy, so let's erase it. Notice that this is the same thing because alpha is E squared. So when I'll get, if you take the difference here, you will get alpha squared here, which is E to the 4th. It's the same expression. But if I write it in this form, I can give you the form for B. And I will not justify it here. Okay, this is the typically a third semester of field theory you compute that. Okay, in any good school it will be done. But I'm sure you didn't manage to do that with SAFE, that probably time didn't permit, right?
You can find a better function.
You didn't compute B, I imagine. Or maybe for QED you did. For QED it's an easy calculation, okay? The question is how to compute it for non-abelian gauge theory. That gets very complicated. Okay, Politzer and Wilczek and Gross got Nobel Prize practically for doing this and understanding what was going on. B, let me write the result. Okay, so this is not really new for you, right? You understand this. Okay. B has the following form. You will see why I'm mentioning it in the same context in a few minutes.
This is for QCD or?
This is for any theory.
Any theory.
And let me specify to SUN now in a moment, but this is for any theory. Any gauge theory in which you have gauge bosons So GB stands for gauge bosons, F stands for fermions. These are contribution to this coefficient B coming from gauge bosons. Coming from fermions. So for example, in QED, this will be the result. I have to define what EF is. It must be related to charge. In a second, right? And the charged particles are fermions in QED. Well, now there is a connection because when Wn is found, that there is of course W plus and W minus eventually, okay? Let me explain what the formula does here. And these are the scalars. If the scalars have a quantum number under that gauge group, this is for some gauge group G, then you should include scalars also. And T is defined like this. T, delta AB, is trace TA, TB, where A and B are generators of that particular representation, of that particular group. Representations may be different. So these numbers may be different. For example, gauge bosons are a joint representation of the group always. Fermions typically up to now were fundamental representation, remember? Or even singlets. And the scalars, the only example we have is the Higgs, which lives in the doublet of SU2 but carries no color, okay? So let's try to see, try to ask me if I forget to say something essential here, okay, Mahmoud?
I didn't get the formula about what do you mean by T delta AB? Like we multiply matrix with number, or?
This is, this.
You mean the element?
Maybe if I put here, it should be, this is just a definition. Yeah, I wrote some T's here and I gave them the number, these are T's. Mm-hmm. And T is just the trace over the generators.
Because
I'll give you an example. For example, if I have a doublet of SU2, tell me what is T?
Zero.
Sigma over 2.
No, generators, but what is T? T is a trace of...
1 over
All the generators are autonormalized. Remember, they must have the same traces when squared, and they should be orthogonal to each other, okay? This is how we... this is hidden in the structure constants of the group. The structure constants are well-defined numbers because of the normalization of the...
2.
1/2. This is spin, it's a half. TA is sigma A over 2. It's not sigma A. It would be 2 if it was sigma A. Well, actually 2 is... If I take a triplet, so sorry, I could have written doublet. I could have gone, so just... T for triplet. So you see the danger of writing, no, I shouldn't write it. Triplet of SU2. What would be T? Triplet is spin 1.
2 over 7.
You can think the following if you don't want to think of matrices. T must be the sum of eigenvalues squared. After all, what will it be? Since they are not too normalized, take the diagonal one. For example, for a doublet, you will take T3, which is sigma 3 over 2, so it's like this. So notice that T is the sum of the eigenvalues. A quarter plus a quarter is a half, by definition of that. It's just a trace of that square. So what about for the triplet? The sum of 2. Why? Because T would be 2, because the eigenvalues are 1, 0, and minus 1, the eigenvalues. Okay, I'm writing like it, right? The T3 generator here now will be diagonal 1, 0, minus 1, and so on. Okay, this is, I don't know if it helps you, Mahmoud. This is what I mean by...
Because I had an idea that T would be a matrix or matrix.
No. This is a number. No, it cannot be a matrix. This must be numbers, okay? This is the product of my... This is this coefficient C that I called here. This is basically hidden in what I call C.
In triplet also, we also normalize the trace to 2 delta
Well,
AB.
yeah, of course.
And in that case, there we will get 2 delta AB.
Yes.
Yeah. Okay.
Yes. Yeah. Well, the generators were, just to remind you, for the triplet, PABC was minus I epsilon ABC. And it's easy to use the properties of this. We can do it explicitly if you wish. After all, then T delta AB would be the trace, so therefore that will be minus epsilon, I don't know, ABC, ACD, AB, CD, something like this, up to sign. I don't know that. We can compute that always. But the simplest way for me to remember is that I look at the diagonal element. Is this completely clear, please? So look, the essence is here. This is the magic formula. Then I will not overemphasize the importance of this formula, okay? We use it to say that the coupling constants run, they change with energies. Notice that this is crawling, not running, because the change is logarithmic and it's very hard to see it. This is one of the reasons why it took such a long time for people to really have these formulas and develop, because we want to be sure experimentally that this is true. So the difference of the coupling constants, the two different mass scales or energies, or the square q square, what we call, whatever, the exchange of momentum, is logarithmic, the coefficient b. By the way, in this formula, when I'm going from the energy mu1 to energy mu2. The question is, I have to include here the particles of my theory. This is very important. The particles that contribute must have the mass which is smaller than mu2. Then you contribute to B. Let's do the other way around. What do I mean? If you have a heavy particle, a very heavy particle, imagine that the particle is infinitely heavy, then it won't contribute, you agree? An infinitely heavy particle basically does not exist. It doesn't move, it doesn't propagate, it cannot contribute to anything. Infinitely many heavy particles, they decouple at low energies. Otherwise there will be no theories of nature. Okay. Right, the W boson decoupled at low energies. You could forget about it. It left a very small effect, which was 1 over mw squared. Okay, so when you went with that mass to infinity, you agree the W boson, there will be no weak interaction if the W boson mass going to infinity. We noticed the other day that if there is a new interaction that will make proton decay, that scale has to be so large that when it goes to infinity, of course, proton is stable. Okay, and up to now, to me, that's infinite. I have not seen it. Okay, so on. So when m goes to infinity, obviously decouples. In this formula, which is approximative, we call it leading log, we ignore the effects of the particles that even lie here. They should be included. They are small. Right? If the particle is infinitely heavy, it decouples infinitely. If the particle is not so infinitely heavy, it of course contributes a little bit. Okay? Do you understand this, please? What I said. The coupling is of course only partial, always. Okay? In this formula, so we ignore the effects of particles with m bigger than mu2. This is an approximate formula only. It's called the leading logarithm. And the bigger is the scale that you're probing, the better is the. It's often called threshold effect. So if you have particles whose masses are not far from them, you better include them, and people do that. Okay, just remember what I'm giving you is just an approximate leading formula. Okay, that's all what I'm asking. But the use of this formula is to say, if I'm looking at the logarithmic change of, say, SU2 coupling constant between, say, 5 GeV and 30 GeV, okay? This is mu1 and mu2. Which particle should I include? Let's think together. Should I include the W boson? Not according to the rule. And the Z boson, right? They are violating the rules. So I ignore this contribution. Should I include the top quark? No. Should I include the Higgs? No. But should I include the tau lepton? Yes, it's lighter than 5 GeV. It's contributing here. I should start including it. Okay. And of course the muon and so on, right? Well, I'll be applying it to some, I'll be using it, okay? So it will become more and more clear. Just remember the heavy particles decoupled. Heavy is defined as the mass larger than the energy scale you're interested in. That's what I call heavy. I have tried very carefully to define heavy up to now. Remember I used to say typically for me it meant heavier than the proton because that was my scale. But sometimes I said I'll change that. For example, if I'm doing experiments at the LHC, heavy is not any more heavier than the proton because LHC can see anything on the order of 100 or 500 or even TeV. At LHC, heavy becomes much bigger than TeV, or actually 10 TeV. Okay, you see the appropriate definition of heaviness is scale dependent, obviously. These are dimension full numbers. Okay. So in order to know to apply this formula, all you have to remember, I will just include the particles that live in that energy domain. Second thing I have to learn, and this is non-trivial, we just started to use this coefficient. Before we go on, notice a profound difference. That the sign here is opposite from the fermions and the scalars. The only hard calculation here is the gauge boson. These things you've done, you can do yourself. This is a trivial calculation. The fermionic and the scalar are similar. The non-trivial thing, the gauge boson calculations are, in the gauge boson calculations you have to include diagrams like this, right? And there are diagrams like this, the gauge boson calculation, the non-abelian which do not cancel, and there are also diagrams like this, and so on and so forth, okay? That was hard, actually. It was.
Why are you mentioning the diagrams here? It's not enough to look at that formula that we define T to calculate T, G, B?
That we define, I'm sorry, T is defined here.
Okay.
Definition of T has nothing to do with this formula. This is a definition of the normalization of the representation. Okay, all the generators must be properly normalized. Okay, this T is the one that you were used to. This is the spin, if you wish, what we call.
Yes. So, but what I mean, what I mean, if we have this formula which is related to T, to find the relationship between the doubling, the running constant
right.
relationship, we just look T that we defined there, right? Can
Sure.
we do this without looking at the diagrams which
Well, you don't have to look at the diagrams anymore because I gave you the formula.
Okay.
These diagrams are the formula is a product of these diagrams, right? There are these diagrams that you have to conclude. The thing that T will appear is obvious because look at this typical, look at the typical diagram. This is a trace of the. You have these two generators and you are taking TA, TB and taking a trace over that. That's what will happen in any of these diagrams. Notice it's no difference. So it's obvious that T will appear. What is not obvious is the sign and the coefficients. There was a strong prejudice that all of this was negative. You know what it means if the sign is negative. So let's try to understand it, okay? and then I'll make some comments. Well, I guess like everything else, you know, the understanding comes from the use, so we try to use this. Okay, let's try to do this a little bit more today so that you are not scared of this. First, notice that if B is negative, what does that mean? That alpha of E2 or mu2 is bigger than alpha of mu1. I have ordered these scales. So the coupling constant will grow with energies. As you go to higher energies in QED, the coupling constant gets bigger. If you go to shorter distances, often called as charge screening, okay, we can comment on that later, I don't want to do it now. If B is positive, then the opposite happens. So you can imagine when people realize this, that the world went crazy. This was the great revolution in the early 70s, when this was realized. And it's amazing that there was this incredible guy at HOF, who not only has done this incredible work of proving that the spontaneously broken gauge series are renormalizable, he was at the same time, he was just a little later working with his advisor Weltman on proving that gravity is not renormalizable, conventionally speaking, doing the usual loop expansion. But meanwhile, he had actually calculated its coefficient. This is an extraordinary story. And he was very busy, and his advisor discouraged him to publish it, okay? And this is actually, he went through, there was a conference in Marseille in 1971 or 72, when someone said it would be nice to find the example of relativistic theory, a realistic theory where B is positive. So, you know, he was a graduate student, and he said, well, I did it. And he didn't publish, you know, yet another, he almost didn't get a Nobel Prize, okay, and there surely would have been a Nobel Prize, okay. He showed it to Zimanski, who was asking the question. He was a year later, the work was published by Wilczek, Gross, and Politzer. Wilczek and Gross working separately from Politzer, okay. Because if this is positive as it is here, and look, the coefficient is large, then B may end up being positive. With computed for QCD. And that means that if I go to higher energies, the coupling constant becoming smaller and smaller justifies the picture that I've seen, that the quarks behave as free. By the way, why do we think that quarks behave as free? What is it? This is the way the quarks were discovered? Deep inelastic scattering. People decided to, if you know, they would study first the elastic scattering, in which the exchange momentum is in the order of the scale of the mass of the proton and neutron. And then you understand that these are extended objects, right, whose form factor you can compute. But if you want to see inside, you need a high resolution, so you need the energy which is much bigger. So deep inelastic meant that deep inelastic. I'd like tomorrow to remind you of that, because you seem to remember. But we'll try to remind ourselves of the salient features. Means that the momentum exchange Q squared deep inelastic means I hit the proton with the electron that carries momentum Q. Here is my proton, and let's imagine it made out of 3 quarks that produces whatever it produces, X. So Q square is defined as minus Q square, and Q square is much bigger than M proton square. Is called deep inelastic. And what happened, okay, this was a great work of Jochen, who realized what to look for, assuming that the quarks will be made out of these partons, they call them, you know, free spin 1/2 particles, which of course are quarks today. And it worked very well. Okay, this is something called scaling, if you remember. In this process, actually, there are 2 variables. One is Q square. The other is the momentum P times Q. Right? Because P prime is not an independent variable anymore. So if I look at the system here, I have two physical variables. And in general, whatever I compute, the cross-section, whatever, should depend on these two variables. It turns out that you can show that when q squared is very large, that the only thing that matters is q squared divided by 2p times q. The properly defined kind of analogs of the form factors, okay? The functions that define this cross-section depend only on x. That's called scaling. It depends on the scaling variable. Doesn't matter what q squared is or p times q, it only depends on the ratio, okay? Let me remind you tomorrow of that, okay? I would lose the floor if I do it today. So, this is sort of the first fundamental step towards QCD. Now that I know that non-abelian gauge series behave like that, the idea that you should gauge color, after all, they come in 3 colors, and if you do that, you will have a theory according to which the coupling also becomes smaller, becomes irresistible. It is interesting, this is 72, 73, what various groups said about gauging color, including Gross, Wilczek, Politzer, Gelman and collaborators, Weinberg, and so on. This is 73 roughly. But in 66 already Nambu suggested to gauge color in a talk in a conference without even knowing all of this. Okay, there was a great intuition. Nambu is the father of the color. Han and Nambu are the people that suggested color to understand the So let's erase this. This was a small reminder. And let's try to understand how we would use it. For example, now, with this in mind, knowing the fact that there is color and that I'm going to gauge it, okay, let's see, there are 3 colors. So what would be the minimal theory of 3 color gauge theory? I want to always do, once I have an idea, the minimal realization of that idea.
SU2 has 3 generators.
SU2. It would be natural to call it SU2 or SO3. Let me call it SO3 because there will be a vector representation of it, if you wish, just to make it. In other words, the quarks will be a vector representation. Quarks have 3 colors. They are not a doublet of SU2. This is the let's call it color, right? And why? Do you know what QCD is? Is it SO3? SU3, which is not minimal. So why was SO3 not chosen? What was realized, well, immediately in nature is that there are no free quarks. Nobody can solve here quarks, right? Well, let's see what was seen. The states that were seen as 3 quarks, Q, 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 and Q bar Q. But no Q and no QQ states were seen. If I have SO3 theory, that means the Q transforms as O times Q. That will be a column, the way we wrote it, in SO3, where O transpose is 1. But notice that Q transpose Q transforms into Q transpose O Q, which is Q transpose Q. This will be invariant. By all the logic, we have proclaimed a confinement of color because we don't see color states. In other words, we don't see states like quarks and quarks, but this will be a color singlet. So there will be a miracle, there will be a very strange puzzle, unexplainable. Why is it that I don't see QQ? QQ is actually color singlet, okay? The rule of the game is we have only seen color singlets in nature, so it cannot be SO3. It's too small. You see, minimal means minimal but realistic. So I try next SU3 color. So I say that Q, any quark, transforms as U times Q. U dagger is U dagger U is 1. So in other words, Q, what I mean by Q is a column. Let's say Q red, Q yellow, Q blue. I don't know which color. Red, yellow, blue. That's what I mean by a quark. This is a quark. Notice that Q bar Q transforms into Q bar U dagger U Q. This is Q bar Q. So this is a color singlet. This is good. I observe color singlets, right? These are called mesons, pion, kaon, and so on. What about three quarks? That's epsilon ijk, qi, qj, qk. That transforms into epsilon ijk, ui prime, ujj prime, uqq prime, ukk prime, qi prime, qj prime, qk prime. Agree? In other words, I'm saying qi transforms into uij. What is this? This is called determinant. This is epsilon I prime, j prime, k prime, determinant u. qi prime, qj prime, qk prime. But this is epsilon ijk, qi, qj, qk, as long as determinant u is u1. This is why it's SU3 and not U3. It has to be SU3. What we have to see now whether this is positive or not, we have to now verify it. It's hopeful, but it's not guaranteed because I have a lot of fermions. You know, if fermions may accumulate and kill the impact of gauge bosons. The idea of QCD that this is an unbroken color symmetry gauge serial nature. Okay, no indications of gluon mass, so we are assuming that the mass is zero. The same way we're assuming that the photon mass is zero. Okay. The limits are far from being that good in the case of the photon, and there are some strong indications that confinement works. Nobody has proven analytic confinement, you know that, okay? There is a major prize offer of £1 million, I think, who would give analytical exact. We don't believe that it will be possible. It's a strongly coupled theory. We have to find ways of computing that. That's called lattice. I'll comment on that tomorrow. But the thing is that there is a deep belief that they are massless, okay, but no proof. So I will, from now on, just as the kind of the photon, assume that gluons are massless. So we now agree, right? SU3 would guarantee that I only see QQ bar and 3 quarks. So how do I compute the B? So this is often called B strong, or B color, or B3. The B associated with SU3. S for strong, C for color, 3 for SU3. Now, how do I compute TGB? Let me see, how would you do it? One thing, I can look it up. SU3 is defined as, well, TA is lambda A over 2. I know lambda matrices, I go and compute the structure constants. No, this is not enough for lambda matrices. Lambda matrices, that's a fundamental representation. Remember, the fundamental representation will always be normalized the same way to a half. I can call this T doublet or T fundamental in any SUN group, because any SUN group has an SU2 as a subgroup, and you must preserve that normalization. And we have specifically done that. We have taken lambda 1, for example, to be like this, sigma 1, and so on. This normalization that is done in SU3 is simply because you must preserve the relations for the SU2 subgroup. Okay, so if I ask you in SU5, you will do the same thing in SU5. You will have to put only Pauli matrices, okay, because you must preserve the normalization. So fundamental representation, for example, if I ask you what is for the triplet, T fundamental will be a half. That's easy, because any SUN group. But how to find the adjoint? I can look it up, those F structure constants, find the trace, no? And I'll find the number, but we don't want to do that. Imagine doing it in SU5 and so on, okay? So here is a little question in group theory. So what is the adjoint? In other words, gauge bosons. Okay, let me say gauge bosons. TGB is by definition T of the adjoint, always. What is adjoint representation in SU3? Is it not? 8 times 8. There are of course 8 matrices always. The number of matrices doesn't change, but they are 8 times 8. Adjoint representation. Adjoint representation, let me remind you, TA BC is minus I FA BC. It's terrible to work with that, so we introduced a trick. We said that we'll work with the adjoint representation to transform. We'll take it as a 3 times 3 Hermitian. I wanted you to tell me. Instead of working with 8 times 8 awful space, I introduce A adjoint representation as TA phi A. I expand in the basis of my Hermitian traceless generators, and with this I know that A dagger is A, so FA is real, and trace of A0, so there are 8 of them. And how does A transform? This is equivalent to this, UA U dagger. It's a trivial exercise you see immediately, right? Because this will give me the commutator, and the commutator will produce F. Okay, we've said this repeatedly. You can work, instead of learning these structure constants, forget it. Just think of this as a Hermitian matrix. The transform is U dagger. U is the U fundamental, the one that you know. Kerman matrices, Pauli matrices in SU2. The question is, how do I find that T for the generators, okay? It's not sort of trivial from here to find it. Well, let me see how much you remember of SU3. I mean, your first encounter with SU3 was with what in particle physics? the A-tot way, right? The reason that the quarks were introduced, they gave us immediately the classification. If I think of the mesons as Q bar states, I get immediately the famous picture of the octet of mesons. I have pi plus, pi 0, pi minus. If I plot here the I3 or T3 of isospin, I will have a triplet of ions. I can plot strangeness here. Sometimes people would write hypercharge, okay, but it's not the hypercharge of weak interaction, it's strangeness. So what do I get then? I have a doublet, K plus and K0. No. K plus has strangeness, so K0 should have the same strange, K0. So if this is 1, this should be a half. Right, T3. This is a doublet. And minus a half. And it becomes sort of like this, right? And then there is another pair of their antiparticles, right? Which should be K0 bar and K minus. That's 7. What is missing? There is a guy called eta, which is a singlet. This is a singlet under SU2. Singlet of SU2. So in other words, this octet of mesons of SU3, I can decompose it under SU2. And I should always do that. I remember, if you want to learn group theory, learn SU2. Because when you know SU2, you know group theory. Everything is made out of SU2. So if you learn that you should immediately go and think of decomposing, okay? So if I ask you tomorrow to construct an SU5 theory, you just say, oh, where should I put those Pauli matrices, okay? Because there is SU2 inside SU5. Kind of things that I will talk to you about. So this will be a triplet. Here it is, pions. Right? Plus, there's a doublet. There is another doublet, or I can write 2 bar. But remember, SU2 is pseudo-real. Doublet and anti-doublet are basically transforming the same way. Plus a singlet. Correct? So if I ask myself, what is T for the octet, which is the adjoint? Which is this trace of whatever the generator was, square, one of them. Notice that these people live in different spaces of SU2. This must be true. Is that clear? This is what I mean by this 8 times 8 matrix. Inside there is a triplet of SU2, which is 3 times 3 matrix, okay, which adjoint with add to R.
So it's like having 8 times 8 matrix with block diagonal matrix.
Precisely. They will be block diagonal because they are orthogonal to each other. Pions and kaons and anti-kaon. Precisely. One way of saying it, is that, so I start with this. I say that 3 is 2 plus 1. Nobody can object to it. I'm doing the same decomposition, okay? No me right anymore. SU3 I'm decomposing in SU2. So what is a joint? A joint, remember, is 3 times 3 bar. Look at the way it transforms. UAU dagger. I'll take it traceless, okay? So this is 2 plus 1 times 2 plus 1 bar. But 2 plus 2 bar can give me a triplet or a singlet. 2 plus 2 bar. Spin, half, gives you spin 1 of spin when you multiply. Then 1 plus 2 is 2 bar. 2 plus 1 is 2, and 1 plus 1 is 1. This is this 9 states. But we are looking at the traceless piece, the 8 of them, okay? I'm saying the same thing. I can always think like this, okay? That this is 3 plus 1 plus 2 bar, which are separated from each other, which are block diagonal. So when I look at this T, this is just the trace of that thing, square. They are gonna add up.
What we talk about here is the SU3 of a flavor, not the color, but basically we use it just like we...
No, I'm not talking about SU3 of flavor. This is just a representation. Think of this, you know, think any which one. This is just a representation. All I'm saying, forget the picture, okay? Now let's erase the picture. This was just to remind you. This is the composition for 3. This is the composition for 8. Of any SU3 in the world. That's the beauty of group theory. The universality of group theory is something so fascinating. This is why we can do everything we want, basically, with group theory. This is why, for example, once I tell you the representation, you know, all the properties of these guys, you know, charges and so on, you know, unlike U1, which is completely arbitrary, the commutation relations of the SUN or group theory in general, the algebras tell you everything about the states which are inside. You know, people sometimes when they talk of minimality of theories, they count the particles. I would never worry about the particles. You should count representations, because one representation is basically, and really, if I tell you that you have a doublet, that's more constrained than a singlet, and surely much more constrained than 2 singlets, because you will get less couplings, because the group theory will reduce the arbitrariness of the question. So a side remark, but I think important. So in other words, what I'm saying that T of the 8 of SU3, oh, I saw it, sorry, of SU3 is 2 plus 1 plus 1 half. Oh, I'm sorry, plus 0, and this is 3.
Why we have 2 in the beginning, not half?
That's the triplet is 2. Spin 1.
But
This is the triplet of SU2.
Okay. What's 3 that down that we was with? Is
2 plus a half plus a half plus 0 is 3.
I mean, the 3 down is 3 of triplet of
SU2, right? This is the decomposition of S. This is SU3,
SU3.
and here is SU2. This is the decomposition of a triplet. This is what you mean by a triplet. A triplet is doublet plus a singlet. After all, look here. Triplet is a doublet plus a singlet. You put a Pauli matrix in the first 2. This is how you constructed the... And this is how you thought about that. For example, in this picture, if you wish, the triplet would be up and down quark and the strange quark. You reproduce that picture by using up and down and the strange quark, and you can reproduce all the properties of that. Strange quark is a singlet of SU2. It carries no isospin. So in the quark picture, the triplet of SU3 global is a doublet plus a singlet. This is up and down quark. This is a strange quark. I'm not talking about now the SU2 of the standard model of the electroweak interaction, please. I'm just talking the composition of the SU3 global symmetry, okay, of strong interactions. And that's the composition. We have this is isospin, so this is isospin doublet, and this is isospin singlet. Okay, this guy is a singlet under isospin. I've learned this when I was studying, but I've learned this every day with every generation, that it's much easier to learn formal group theory than to really understand what is going on in SU2 and SU3. Always remember that. Formalism much easier.
But for
The more formal things are, the less we have to think. But of course, it's discarded mathematically, so we have to maybe compensate with something else. Yes, please.
but for singular, we cannot define T, right? Because there is only
Oh, it's zero.
Yeah.
No, singlet is defined. T acting on a singlet generator is zero. This is the definition of a singlet. A generator is zero. Doublet is a sigma over 2. So T acting on a singlet, T acting on a doublet is sigma A over 2 acting on a doublet. And so on and so forth. By the way, I could just cite the result and let it be, because we don't have to do anything beyond SU3, but now I want you to, because you will be absorb it easier if you do yet another little exercise. So suppose that I ask you, now let me do SUN. How would I compute it for SUN? Tomorrow someone may ask you, okay? This you normally don't find easily in the book, so try to pay attention, please. Suppose that I ask you, so I have SUN, and now I want to do the adjoint of SUN. The gauge boson contribution, or any adjoint, by the way, it may be the Higgs. Doesn't matter which particular fields we are talking about. The T is always ascending independently of the particle. What changes are the coefficients from the particle to particle. Fermions have minus 2/3, scalars minus 1/3, because of their spin that enters into the... When you do these loops, you know there is also the Lorentz quantum number, if you wish, okay? So they enter differently, and this coefficient. But T, of course, is just a group theory property. So if I ask you an octet of T will be the same for the scalars or the fermions or the gauge bosons, please remember that. So what do you think is the T of the adjoint for SUN? It was 2 in SU2 and 3 in SU3. So what is it? It's N. How to prove it? Okay, but what do I decompose it on? On SUN minus 1? Well, so, okay, you're getting there. So let's do induction. And then the composition will solve immediately. Okay, sorry. Maybe if you meant that, then I have nothing to say. So let me assume that T of adjoint of SUN is N. Assume. So then I have to prove that TA of SUN plus 1 is N plus 1. I have to prove this now. So let me put a question mark. Is this true? So what I will do? I will decompose now. I will do what Nicolas said. So now I will decompose the adjoint of N plus 1 is, well, let me do the following. This is N plus 1 times N plus 1 bar, by definition. This is a definition of the adjoint. Remember, the adjoint, the traces part, okay? The adjoint is always, it is hidden. It is given by the By the way, how do you know that? Remember how the gauge bosons couple, you know, it's here. Then you have this matrix of gauge bosons Q. Right? We always wrote it TA. This was our adjoint. Notice that this is n bar times n. This transforms as n, this is n bar. Okay, so this is it. But what is this? This is n times n bar plus n bar plus 1. This is A of n plus 1, because I take the trace as part. This 1 I don't care about, plus n bar. The decomposition that I use in SU3, this one, is this one. A joint of n plus 1 is a joint of n plus n bar plus a singlet. This is always be true. Read it in SU3. A joint is an octet, it's a triplet, plus a fundamental, plus a fundamental, plus 1. But that means, and this I assumed was n, this is 0, this is a half, this is a half. This is precisely n plus 1. We proved.
What is in the right side always in SU2? So we have AN in SU2 or?
No SU2, SUN.
SUN.
And induction. What does induction mean? I assume that T of SUN is n. Induction works like that, right? And then I have to prove it for n plus 1. This is what you've done.
Yeah, but I'm speaking about the decomposition there.
Right, this is SUN. There's no SU2 anymore. I'm working in SUN. I assume that SUN is n, and I've checked it.
Yes, but
I double checked it actually. I've checked it in SU2 and SU3. I didn't have to. I could have started just with SU2 and immediately written this formula. And then I composed the adjoint of n plus 1 into the adjoint of SUN. This is the adjoint of SUN plus 1 decomposed here into SUN. Why SU2? There is no more SU2.
Why we put n in bar half? Why we put in half?
Where? Which line?
The last one. Like
here.
Yes.
Because the fundamental representation, this is a fundamental representation of SUN. They are normalized always to a half.
Okay.
T, I've said here, but I didn't emphasize. Okay, let's remind ourselves. This will be appearing throughout your, in SUN, T for the fundamental is a half. Okay. It must be, because SU2 is a subgroup of SUN, and you must normalize the same way. We said all the generators should be orthonormalized. So that means the SU2 subgroup will be orthonormalized. It's orthonormalized to half, so the rest have to orthonormalize to half. Okay. So T fundamental, and now I even learned that T adjoint is N. I have all I need. I'm lucky that I have all I need. There are other representations, but they are not realized in natures in the theory that we are talking about. You know, there are complicated representations, symmetric ones, and so on. But you can always do that by decomposition. So if I ask you what is the symmetric representation of SU3, what would be a symmetric representation? You know, I said that 3 times 3 bar is 8 plus 1 in SU3. But there is also 3 times 3, for example. What would this be? You symmetrize that 6 and by time symmetry turns out to be 3 bar, similar to 3. So if I ask you what is the T of 6, how would you do this? let's just one more comment just to see how you would do it. I don't have sextet representations of SU3, fortunately. But they may appear in some theory beyond the standard model. So how would you do this? Well, remember how I reason. I always thought that 3 is 2 plus 1. So 3 times 3 is 2 plus 1 times 2 plus 1. So 2 plus 2, so I have 3 plus, and so on. I decompose it, then I recognize my decomposition of 6, but I don't want to do it now. I let you as a little exercise, so if you want tomorrow, you tell me, I've calculated T of 6-dimensional representation by decomposing it in SU2, because in SU2 you know everything. So whenever in doubt, go back to SU2, struggle. Even in SU5, if you didn't do it, just think of how you would decompose it in SU5. But okay, we'll come to that if you come to that. Let me not go on. You do that. Okay, compute T of 6, for example. This is typical exercise that you get when your new theory, you're working in some new grand unified theory, and inside there are even 6-dimensional representation that maybe one day we will observe. We didn't yet now. Okay. So I know now. So let's now compute P3. This was SUN was a digression. I want to compute B3. And I know that B of the gauge bosons was 11/3 times 3. Right? And it's 3 for SU3. So that's 11. This is the gauge boson contribution, okay? 11/3. I never derived this coefficient, okay? This is but it's interesting they got a Nobel Prize, but now a PhD student does it. At CISA, this is what you will do next year. Those of you at CISA, you will compute P3. Talk about Nobel Prize. By the way, to understand what was going on was a profound issue. It wasn't just a calculation. There are also fermions that we call quarks. When I say here, by the way, when I write this formula, when I talk about fermions, I mean the fundamental fermions. I mean the irreducible representation of Lorentz group as I always did, which means left and right fermions. You have to separately compute them. I mean two-component fermion. I mean, as I always did, the basic states. Not the way Dirac imagined putting them together, okay? So which particles do I have in QCD? I have an up quark, left-handed. I have a right-handed up quark. I have a left-handed down quark and a right-handed down quark. And then, of course, I have generation by generation. Okay. So let's think of one generation. How much does this contribute? They are fundamental representation of SU3. They have 3 colors. Each of them is a fundamental of SU3. A T of the fundamental is a half. Sorry? Oh, that's a Cavendish coefficient. No, first T. No, first I compute T. No, first I have to know T, then I include the combination. So T of one generation, let's call it, if you don't mind. This is a generation, up and down quark. Electron has no color, neutrino has no color, so I'm actually computing the whole generation of fermions. This is 2. So in other words, the B3, let's now write it. 11/3, I will repeat it again, times 3, minus 2/3 times 2 times number of generation. Each generation has a factor of 2. This is often written in the following sense, so this is written as 33/3 minus 4/3, so 4. It's often written in this way. It is often written as 33 minus 8 number of flavors over 3. Flavors, we say that this is one flavor and this is another flavor. Remember, color is orthogonal to flavor. Flavor is what weak interactions change. Okay? We'll have to say a few words about these strange gauge bosons. I didn't even talk about the physics that they do. I will do that in the moment. I'm still at this point more mathematical than physical. Well, maybe to some degree both. So you agree, right? This is number of two number of flavors. Okay. Flavor is up and down. So if they ask you what do weak interactions do, they change flavor. W boson, for its living, changes up into down. What does a gluon do? Changes color. Gluon sees a red quark, makes it yellow. Another guy sees a yellow, makes it blue, and so on. Okay, or sees a red, or makes it blue, because you know the direction. Okay. This is when I speak of weak interactions, I can ignore color, because they end up. You know, when I wrote U and D, really what I mean that this was like this. Red, yellow, blue. So the double boson acting this has nothing to do with the color. I could ignore it, okay? And when I speak of gluons, I can ignore the flavor completely, because the gauge boson will take this, and so on. But it will not touch the flavor. A gluon cannot change the nature of the quark. Up quark stays up quark, just like the photon. So this is my B3. So notice that B3 is positive as long as there are not many generations. So QCD works. There are various miracles that make this beautiful theory. This is an extraordinary theory. The simplicity and the richness and the depth of this theory cannot be overemphasized. We'll keep talking about it. Is lying into the, another miracle. If I have a lot of families, I wouldn't have asymptotic freedom, and this picture would break down completely. Okay.
Is it 2 or 8? The last one.
8.
Number of the fermions or
flavors.
Flavors.
Flavor. Think of that as a number of the fermions which come in colors. You can also think that, but think of flavors or quark flavors. Fermions wouldn't be, because electron is a fermion, if it doesn't come. So this is, flavor is just, okay, generation up and down are 2 flavors.
Oh, but I mean, for generation we have 3. And for flavors we have 6, right?
What do you mean we have 3? We have 3 colors. But I cannot count color anymore there. Color entered here. Color entered here, then you stop counting color.
When we said that we have generation, we said we have 3 generations. We consider this to be first generation?
No, n generations we say we have. I don't know whether we have 3 generations. There are strong indications, I told you. We have almost proven that, but let's wait a little more to be sure. LHC is increasing the energy, okay? I gave you various arguments why it all indicates that there are 3 families. I want to have a general formula that depends on number of generations.
I'm speaking about the relation between generation and the flavor.
Well, every generation has 2 flavors. This is a 1 generation. It has 2 flavors, up and down quark flavors. This is what I told you. This is called flavor going. The vertical component is called flavor. Neutrino and electrons are flavors. Weak interactions change flavor, strong interactions change color. Okay, this is just counting the quarks, if you wish. In this case, it is the number of fermions which are quarks. Count quarks. So, this formula has a fantastic agreement with the experiment, okay, because it's not just, you know, we usually include threshold effects, which I said, you shouldn't just think of the heavy particle completely coupled. You should also go beyond one loop. People, they do this, you can do the two-loop correction and so on, okay. One of the successes of QCD is the well function for this formula, B3. Now I know how, so let's specify let's conclude. Let me tell you what is often done. So 1 over alpha strong and mu2. Let me write now energy. Often you write this at the energies. Minus 1 over alpha strong at E1 is, what is the, is 33 minus 2 number of flavors or quarks divided by 6 pi logarithm E2 over E1. I wrote with energy just for fun. Think of mu, think of energy, think of... In deep inelastic there will be a square root of Q squared. So, the following is, people wanted to look, so the picture goes like this. Okay, obviously it's falling down with energy, right? This is possible.
This is 8 or 2?
Here?
Yes.
8. 4 times 2 is 8. Each generation? Okay, if you insist. Okay, reasonable. All 8, I put 8.
But we have 6.
Remember, you know how reasonable.
Yeah, but we have 6 flavors, or we have 6 flavors, right?
We have 6 flavors up to now. I'll be more specific, okay? Yes, up and down. Charm is strange.
We will get a negative number, right?
No.
1. We put 1 or...
So did I make a mistake? 4. Oh. Maybe this is better. Thank you. This is what's bugging you, Mahmoud. I'm sorry, I didn't appreciate it. You should have been more, you know. Thank you. Of course, if there are twice as many, you're right. I doubled them. Oh, this is great. You see, the fear to say you are wrong. Okay, you know, it's not easy. When you doubt yourself. Okay. Thank you. And you see, I have somehow remembered the formula, so I wrote the correct formula. So now, look, if I'm going to higher and higher energy, and this is what people saw when they studied scaling, you know, when they saw quarks as free. By the way, here you can do a beautiful thing. You first do them as free, and then you do the corrections, because they actually have interactions with the gluons, and you correct that scaling, okay?